Good morning and welcome to today's webinar, Improved Flare Operations and Emissions Quantification, sponsored by Panametrics. I'm Chris Smith with Oil and Gas Journal. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, please put your question in the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the OGJ website within the next week. You'll be notified by email when the archive is available. And now I'd like to introduce today's speakers. Hunter Wiley is Global Product Manager of flare.IQ and Sentinel for Panametrics, a Baker Hughes business. Hunter joined Panametrics in 2015 as a field service engineer for the North America service team. He performed regulatory service across a wide variety of Panametrics liquid flow meters, gas flow meters, and process analyzer equipment, before advancing to the global services teams as the technical specialist, providing support and standardization for all regions. He is currently Global Product Manager for flare.IQ, a flare management tool important for smokeless operation and emissions quantification, as well as for Sentinel Flow Systems, a high accuracy liquid flow platform with OIML certification. And Gerard Bottino is also joining us, a Global Flow Commercial Development Leader for Panametrics, a Baker Hughes business. Gerard joined Panametrics in 2008 as a flow product specialist for Europe, the Middle East, and Africa, and is now the Global Flow Commercial Development Leader. He started his career in 1990 in the process industry after receiving his Master's of Science, and before joining Panametrics, held technical and commercial roles in several industries. Gerard is a subject matter expert in flow, field of instrumentation, and process industries. And with that, team, over to you.
Thanks for the introduction, Chris. Let's go straight to the agenda for today. So we're going to go through a quick intro. Afterwards, we're going to kind of remind everybody the fundamental about ultrasonic technology and flare flow meters. And then we will go a little bit deeper into the flare.IQ solution we offer. And Hunter will hand over I hand over to Hunter for the flare.IQ testing. And it will cover the tests we have done together with an international oil company, as well as the existing and upcoming regulations that are kind of touching the flare and their emissions. And we're going to end up with, let's say, 10 to 15 minutes Q&A for you to get an opportunity to ask your question and get them answered. So with this, the intro itself is to introduce Baker Hughes. So Baker Hughes is an energy technology company. So the motto of the company is to get the energy safer, cleaner, and more efficient for the people on the planet. And for us as a Baker business, we are focusing on flow measurement and gas and moisture measurements. For decades, the company was founded in the mid-60s and still very solid these days, with a strong reputation on tackling the very difficult applications. So with that being said, we're going to get into the hot topic of the moment. everybody focuses on their carbon footprint. In other words, everybody wants to know the greenhouse gas emissions that they emit as part of their operations. So I've used a nice graph that showcases the impact of the so-called global warming potential for 100 years of methane when you compare it to carbon dioxide. So carbon dioxide is a base of 1, and the methane is a base of 28, which basically means that the methane is 28 times more harmful to the environment than carbon dioxide is. So I couldn't find a more recent graph. The 28 comes from the 5th assessment of the Intergovernmental Panel for Climate Change. Is a kind of United Nations organization. And on the latest release they did on August 24, it's now 27. And you can see that on the graph underneath, but it doesn't change much. I mean, 27, 28, it just means that it's quite harmful as a gas. So what are the greenhouse gas emissions by species? So number one is carbon dioxide, right? So 3/4 of it comes from carbon dioxide. The second biggest is methane. The third biggest is nitrous oxide. And the last one, and not the least, is every fluorinated gases. So if you do the math, you will realize that it doesn't add up to 100 just because of rounding. But it just to highlight where those greenhouse gas sources are coming from. And then you have another one that highlights the breakdown for sectors, industries. So electricity and heat generation is by far the biggest contributor to those emissions. The second biggest is transportation. And if you look at the energy industry by itself, it's very minimal, only 4%. And if you look at fugitive emissions, it's about 9%. So obviously, if you were to look into the details, I have the sources mentioned at the bottom of each graph. You will have different breakdown depending on countries or continent. So just be mindful about that. It's an average for the globe. So that set the tone as why we need to focus on these. Our today's topic is about flaring. So why flare is a source of methane? Well, it's very simple. It's because while we could expect that everything is being combusted at the flare tip, the reality is not. So for a number of years, it has been agreed and assessed that about 2% of the gas that is being flared remains uncombusted, which in other words means that there's a so-called methane slip that goes out of the flare tip. And there's another assumption that is made is that flares are always kept lit. So they always have a flame, a pilot, even if there's no flaring at a given point in time. So that when any hydrocarbon gas gets out of the flare stack, it burns. So based on those assumptions that have been in use for decades, the World Bank estimated that in 2023, so basically last year, 381 million tons of CO2 equivalent have been released into the atmosphere. So CO2 equivalent means the CO2 itself coming from this combustion plus the methane slip with its 100-year global warming potential, right? So that's basically to give things in a very good picture of what is at stake. Now, the question to the operators that, do you know your flares? In other words, that means, do you know what you are flaring and what are the emissions that are consecutive to those flaring events? It's also fair to say that if people are following the World Bank Global Gas Flaring Reduction Initiative that kind of forbid routine flaring by the year 2030, which is not very far from now, it can be a bit different. That means that in normal operation, there's no flare at all. But they are still flaring because it remains a safety device, so that if there's an incident on a production facility, a refinery, an LNG plant, then the gas is being released to the flare to be burned. So before getting into the flare.IQ details, we need to get back to the fundamentals of ultrasonic technology. So this is an example of a meter setup. We didn't want to bother you with any kind of equations, but just to remind everybody the working principle. So a transducer is embedded, in which is embedded a crystal piezo, generates an acoustic pulse that is kind of sent, and the transducer will alternatively work as a transmitter and a receiver, not at the same time, alternatively. So for instance, the one, if you flow from left to right, the one that is upstream, say that at a given point in time is the transmitter, it transmits the acoustic pulse that will reach the downstream transducer, which will act as a receiver. And then the downstream transducer will generate an acoustic pulse that will move towards the upstream transducer, which in turn will receive this pulse. So from left to right, you have the green arrow, and from right to left, you have the yellow arrow. So when there's no flow, the time it takes for traveling one side to the other is the same, regardless if you go from up to downstream or from downstream to upstream. When there's flow or velocity, then you will have a time shift coming from this difference because the green arrow will be accelerated with the flow, whereas the yellow arrow will be decelerated with the flow. This time difference is directly proportional to the velocity of the fluid. And thereafter, when the velocity is calculated, then you multiply it by the cross-section of the pipe to get the volumetric flow. That's basically a very simple working principle. So in real life, how does it look like? If you look at the top two left pictures, you will have, let's say, sizable flare meters. One is with a spool. The other one, there's no spool, it's a tap system. That means that the line has been drilled. It was existing, there was no equipment there. So there are many ways to install flare meters. And the two other pictures on smaller sizes are typically used on unconventional fields. And we have seen in the field kind of huge differences in terms of pipe sizes, ranging from 2 inches for the very small lines. And the biggest we ever did is 116 inches. So massive. For the people educated in metric, is almost 3 meters diameter, down to 50 millimeters up to almost 3 meters in diameter. So that's very, very big in terms of pipe sizes. The other thing to know is that you need a little bit of straight runs before and after the measurement point to ensure that you have a velocity profile that is nicely distributed. We don't really, it doesn't really matter if you are laminar, turbulent, transitional. What we need is to make sure that the flow profile is fully developed, right? In certain circumstances, it's difficult to get the needed straight runs up and downstream, typically 20 diameters, nominal diameters before and 5 diameters after the measurement point. So it's more and more common for us to use computational fluid dynamics to kind of make an assessment of the flow contour, and from there make a recommendation as to which position the flare measurement points needs to be installed, as well as the path setup. As you can see on the middle sketch, there are many different ways to install the flare transducers, and we have different methods. We have a very long nomenclature. It's a kind of a simplified sketch. So to optimize the installation so that we minimize the effect of a non-fully developed profile. On top of this, we have also challenges to address with a very large turndown ratio from very low flows down to, let's say, 0.1 foot per second, up to, during blowdown conditions, 400 feet per second, which is extremely high in velocity. So temperatures can also range quite big depending on the applications we are in front. And also upstream, so in production facilities, sometimes reservoirs, they contain a high content of carbon dioxide, which is a bit difficult to handle because it's not nutritive gas for ultrasonic signal. And if you go to the downstream side for any kind of hydrogen process units, like hydrocracker, like hydrotreater, you will have also a potential high content of hydrogen available at site. So the first thing you need to ensure that your flare flow measurement is correct. That forms the basis of a good working system. So now if you go to the next level and you get into the flare.IQ. So flare.IQ exists in different configurations depending on the configuration is available at site. So this kind of sketch features a typical upstream application where there's no assistance. So you simply have the main flare line getting into the stack where the flow meter is normally installed after the knockout drum. And it connects to the distributed control system where it is fed with information coming from the flow meter. The flow meter measuring the flow of flare must be an ultrasonic flow meter, because not only it gives the volumetric flow rate, it also calculates the sound speed of the gas mixture being put into the flare line. So this is not available with any other technology. So we do need to have an ultrasonic flow meter into this flare line. So it's not represented here, but we also need the pressure and the temperature close to the measurement point, as well as the wind speed from the weather station. And if it is available, that's not very frequent, but we see that more and more, an analyzer to have the different species getting into the flare. If there's no analyzer, the system does work, but if you have inorganic gases, it may help to reduce the uncertainty of the algorithm. So the distributed control system itself will then communicate through a Modbus TCP/IP connection to our flare.IQ, which is essentially an industrial computer that will take the data from the DCS, ingest them, compute them, and in a matter of a handful of a second, will output the net heating value of the combustion zone, the combustion efficiency, the destruction and removal efficiency, the carbon dioxide, the carbon monoxide, the volatile organic compounds, and the CO2 equivalent. So that can be stored into the DCS so that in case of audits from environmental regulators, it can be shown as how it has been tracked on a 24/7 basis. So as I mentioned earlier, sometimes if you were to comply with the global gas flaring reduction, you would probably need to have zero routine flaring. So if that's the case, you will have no flare during normal operations. It means that you need to remain safe and therefore to prevent air to get into the stack itself, because air contains oxygen, obviously. So in this case, you will need to have a purge flow Sometimes it is with gas, but it's very rare. Most of the time it uses nitrogen. Nitrogen has no calorific value, obviously, that's an ionized gas. And if there's nitrogen purging, we need to know what the nitrogen content is. So either there's a single point of injection, and at this point in time, we have a flow meter that determines the volume of nitrogen that is being put into the flare line, or if it comes from different angles, we will need to get this analyzed at some point. So that's for the non-assisted system. When you are in the control room, you will have a human machine interface that looks like this. On the left-hand side, you have the different tabs where you have everything for configuration purposes, but from an operational point of view, what you will be interested in will be this kind of screenshot. You have on the left column all the CE percent, DRE percent, VOC, mass, CO mass, CO2 mass, and CO2 equivalent mass. The flare inputs, if there's, again, nitrogen, the flare flow, temperature, pressure, wind speed, and sound speed of the gas mixture. As you can notice, everything is set there in metric units. Obviously, we can configure it either in metric or imperial. The system comes pre-configured to fit your needs. And then you get the net heating value. And if you see such a high net heating value, even without looking at the emissions, you already know that you're going to be quite high in efficiency. So that's for the non-assisted system, because on the top right, you can see that assist type is none. Now, in real life, this is what we have experimented together with an IOC offshore and an FPSO, where they were monitoring the HP and the LP flare. And you could see that they were using before the kind of magic static emission factor of 98%. And they realized that they were actually combusting at a much higher efficiency. And getting from, to put things very simple, from 98 to 99, you have your methane emissions by, you have your methane emissions. So that's significant. So this is a very good learning that in reality, when flare are non-assisted, they can combust very efficiently. Now, if you were to pay for this, I did some calculation based on $15 per metric ton at a flow rate of 37.5 thousand cubic meter per day. That's already almost $500,000. So in $15 per ton, it may look high, but in some countries it's much higher than that already. If we were to go onto an assisted flare with only air, these type of flares are seen sometimes in production assets, but also quite often in LNG facilities. So the only difference with what we've seen before, in that this time you have an additional line, as you can see, air, that is put into the flare tip to increase the amount of oxygen if the gas becomes too rich. So the system works the same way, but on top of outputting the emission values, you can also have a live control of the input of air. In other words, you will have the set points calculated for the control valves of air to be sent to the DCS, so that the DCS itself moves the valve on a live basis to get the optimum combustion at the flare tip. If you go downstream, this will be this kind of setup where it's rarely air, it's more often steam, and sometimes it can get pretty lean gas, unlike the production facilities. So it's not uncommon to see a fuel gas line that fits the flare line to increase the net heating value of the gas mixture. So the overall concept remains the same, with everything being fed by from the instruments to the DCS, and from the DCS to the flare.IQ, which runs its algorithms. And in this instance, will also help of getting the right set points that will still be piloted by the control system to trigger the control valves to get the good amount of oxygen needed to optimize the combustion. So what we've observed in downstream assets, there's a strong tendency at oversteaming. Well, sometimes you can be also getting through an incident and being into this kind of configuration where you are having quite a bad black smoke. And I can assure you that this picture is not photoshopped. It's an actual picture. I will not disclose where it was taken, but it's an actual picture. So in lots of countries these days, if you have this kind of flare behavior for more than 5 minutes, you will get fined by millions of dollars. But on kind of normal operations, it's also not infrequent to see these kind of flares where it seems that the smoke, there's actually steam getting out of the flare tip, and you might still have a little bit of combustion, but in this instance, the combustion drops down to the likes of 60, maybe 50%, and then the methane slip becomes really big, even if the operator may still report as a 98% efficiency, where if you see that, it is guaranteed that it is not. So with that being said, when you go back to the to the kind of console that you have in the control room, what has changed there is that on the top right, you have a sys type as steam, and therefore, unlike what we had earlier, you can see on the flare inputs, now you have a steam flow that was not present when we had non-assisted flares, where it is present there, and this steam assist flow will be moving. If I would have a video there, you can see it moving every seconds almost. And what is of interest as well is that those values are color coded, so you can see that you have green, red, gray, blue, etc. So it gives you a good indication. So even if you don't have a good understanding of what it means in terms of those values on your screen, by just looking at the colors, you have a good feel of whether you're good or not. So with this, we have a polling question for you guys. So the polling question that we're going to ask you, and we'll give you a few seconds to answer this, is what kind of flares are you using at your site? Is it non-assisted? Is it assisted? And so you have different choices. You will need to answer those questions, and based on the answers, we will show everybody what is the answer from the audience. We will leave you a few seconds. So basically, as can be seen, there's 80% of you who mentioned that you have no steam. This has changed quite a bit. So about 2/3 on no steam or air assist, and 1/3 steam assist systems. It moves a little bit, obviously very dynamic, but it's quite interesting though, because it means that most of the attendees today are from upstream in the, it has moved quite a bit, and about 45% is from the downstream, because we don't see steam assisted flares in upstream much. Right, so with this, I'm going to hand over to my colleague and friend Hunter for the testing.
Perfect. Thank you very much, Gerard, for that. Now that we've looked at the basis of what goes into the operation of a flare and the capabilities for flare.IQ on all these different various flares, let's take a look more at the testing that we've done and completed for this emission solution. So here we can see an image of the test setup that was conducted at the John Zink testing facility in Tulsa, Oklahoma. The extractive sampling probe that you can see suspended by a crane is guided by 2 people on the ground. At the funnel, there are installed 3 different thermocouples that measure the temperature of the vapor that's being collected. The reason on this is they wanted to make sure that you were able to have that extractive sampling close enough to the flame, but not in the part of the flame where the combustion was happening. That's obviously where the temperature would be very hot. In those cases, we would see thermocouple temperatures above 700 degrees Fahrenheit, or about 370 Celsius. We also wanted to make sure that we weren't too far away and extracting the ambient air around instead. So we were maintaining a range of that 300 Fahrenheit to 700 Fahrenheit, or about 150 C to 370 C. Any data showing that the probe was either too close or too far away from where that analysis was supposed to be completed was just being ignored and left out, just so that we were looking purely at the plume rather than the flame or elsewhere, so as to not bias the results. You can also see the mobile lab there in the back, just behind the flare, where this analysis is being completed. So let's go ahead, take a look at a wider diagram of this setup and discuss each portion in a little bit more depth. So as we can see here, we have the crane suspending the probe over the flare plume, along with the capture hose leading to the mobile lab. On the right-hand side, you can see the setup that we used to modify the net heating value of the vent gas by changing the flow amounts of the natural gas and nitrogen inlets. We also had used polypropylene to be able to add a higher BTU gas in there at some cases, just to be able to induce some smoking events as well. An FTIR, or Fourier transform infrared spectrometer, was used to analyze the mixed gases and determine the net heating value of the vent gas, both before the burner and after collection with the probe. The mixed gases pass through an ultrasonic flow meter that measures both the flow rate and the speed of sound of the gas. That data is then sent back to the local data acquisition system, along with the wind speed input that comes from a meteorological station that's on site. And then that's all fed into the flare.IQ for calculation of the net heating value and emissions parameters. For those that have some knowledge of how previous tests were conducted by TCEQ back in early 2010, you'll notice this extractive sampling and flare gas energy modulation was conducted very similarly, just obviously with a few more modern components in the line. And even though this is on an unassisted flare, we did take the opportunity to test out a couple of different flare tips as well. So the first that you see here is the standard straight pipe tip. The one that we used was a 14-inch. Obviously, this is probably one of the more common ones that we see for just traditional upstream production fields. Sometimes you may have slightly larger, slightly smaller tips. Obviously, on the refinery and petrochem side, those can range up to very large size tips, but the concepts are still very, very much the same. You can see here too, we have some flame stabilization tabs around that inner edge. That creates a low pressure zone along the perimeter of the tip exit area to ensure that you have slower moving gases that can then be easily ignited by the pilot burner. The second tip you see there in the center is a restricted orifice pressure-assisted tip that increases the exit velocity so that the flame can then be taller and thereby interact with more ambient air in a vertical column above the tip. Of course, that is still a variable tip size. So as you have higher flow rates, you can have that tip become a larger cross-sectional area, and therefore your tip velocity will then come back down. Important part about that is we want to make sure that the gas doesn't jump past the point of ignition. And that's known as sort of this flame separation. Obviously, it's if you have gas that separates past where the combustion zone is, they don't get it fully combusted at that point. The last tip that we see here on the right-hand side is one of the newer multi-arm pressure-assisted tips that manually spreads the flame apart horizontally to interact with more ambient air in sort of this shorter and wider vertical column in the combustion zone. So looking at all these, what were the results? The first plot that we're going to look at shows the energy content of the gas prior to combustion here on the x-axis, with the destruction and removal efficiency, or DRE percent, plotted on the y-axis. The extractive method data points are shown in black, which is the JZ or John Zink data, while the flare.IQ values are shown in red. At the lower net heating value of the vent gas, or NHV-VG, we can see that the DRE suffers tremendously. When the same test was done by TCEQ back in 2010, similar results to what we see here were the same driving factors that shape the regulations to state operators must maintain a net heating value in the combustion zone, or NHVCZ, maintaining that value above 270 BTUs per standard cubic foot. Because this was an unassisted flare tip, the NHV-VG is relatively equal to the NHV-CZ, as there's no additional air dilution or energy reduction due to the introduction of steam. As you can see, higher NHV-CZ provides a higher DRE value. The second plot on the right-hand side shows the comparison of the flare.IQ measured DRE to that of the extractive analysis. Above a net heating value of 300 BTUs per scuff, flare.IQ was within 1%, while around 2 to 4% at lower net heating values. Now, let's go ahead and take a deeper dive into the analysis of uncertainties involved. From reviewing the uncertainty analysis, we can see very clearly the DRE discrepancy between the extractive sampling and flare.IQ gets larger as net heating value decreases based on the plot on the left. There's a strong correlation between DRE uncertainties of both the extractive and the flare.IQ measurements here, largely correlated with a large uncertainty in the empirical measurement, such as keeping the flame stable and lit, as well as the flare.IQ calculation, which can be seen with the steep portion of the curve. This derivation of uncertainty is essential if reported values are to conform with OGMP 2.0 reporting requirements, but we'll take a look at those in a little bit more detail in a few minutes. These uncertainties for flare.IQ calculation have been evaluated using two different methods. One is based on air propagation method, while the other uses a Monte Carlo method. The plot on the right shows the uncertainties of flare.IQ DRE for two standard deviations, or about 95% confidence interval based on both of those methods. The uncertainties from both methods are consistent with each other, shown in the main plot, except for about 5 extreme cases where the direct air propagation method did not have any limit for the DRE calculation that you can see there in the insert. For DRE that's greater than 98%, the uncertainty is 0.4%, or a K=2 value. Though this uncertainty may appear small, it can equate to a substantial difference in absolute methane and volatile organic compound emissions. Our team also dove deeper into understanding the relationship between the momentum flux ratio, or the MFR, for different net heating value gas combinations. This parameter accounts for a crosswind effect on the flare tip velocity that can cause the flame to lie down or appear as what some call a lazy flame. From looking at the equation that you see on the top right, we can see that a small MFR is due to higher wind and lower tip velocities. For flares with more energetic gases, the MFR has very little impact. However, for flares that have an NHV below 300, this can have a significant impact on the efficiency of the flare. Now, just going to say, I've gone through these last slides fairly quickly. I don't want to make you think that this was a simple test with minimal impact for operators or regulators. So for those that have more interest in reading through this study and how we gained the data and analyzed it, I highly encourage you to go through and read through these 3 different academic papers that Panametrics had published with BP. The first paper sets up the methodology of the test and the implications for controlling methane emissions on flares, along with showing the DRE above 98% is possible, though it highly depends on the net heating value of the vent gas and crosswind conditions. The second paper dives deeper into the parametric model that flare.IQ utilizes for reliable, continuous flare combustion efficiency measurement that can be deployed on many flares with minimal physical changes to existing equipment at customer sites. The third paper uses this empirical test data to validate a CFD model, then leverages that CFD model to better investigate the effects for MFR on winds over 100 miles per hour or about 50 meters per second. Now, some of you are thinking, man, that's really fast moving wind. Of course, yes, hurricane force winds may seem a little crazy, but for those that are here in the US, some of you know how that Gulf of Mexico gets in September. But let's go ahead. We'll take a look at a few of these excerpts from the papers. The first one that we see here is the first paper. And from that, we get to see the following. There's actually challenges that are seen in onshore US flares that vary the DRE tremendously from 70 to 100%, despite the desire of regulations for this to remain above 98 in idealized conditions. A shift from the ideal 98% case to a typical 96% case doubles what the reported methane emissions are, while a 98 to 99 DRE halves that reported methane emission. This impact can be significant as operators are beginning to face carbon taxes and more of that rollout, as Gerard had mentioned previously. Methane emission measurement methods may be difficult to conduct and can have high uncertainties. Some more points that we have over here is, though the structure and scope of this testing is well understood and it's been done before, there is currently no standard reference to measure flare combustion efficiency. This has been a large sticking point for many environmental regulators, leading to instead monitoring net heating value, as seen by the EPA's refinery sector rule. One of the key parameters that affects the flare efficiency is your net heating value of the vent gas. For a flare that is above 300 BTUs per scuff, DRE value of 99.6 can be typical with limited impact caused by flow rate or wind speed. A couple of final points from that first paper. Spot check samples may catch the flare on a good day, or in some cases, maybe a very bad day, and assume that level of activity for the full sample period, whether that's weekly, monthly, or annually, whatever the local regs may or may not say. Only continuous tracking can prevent large emission reporting errors. You also have a universal application of that 98% DRE. That value should be revisited with proving reporting methods to provide defensible emissions reductions. With a look at the second paper, a couple more key items. The introduction of the parametric model developed by Panametrics to account for all influential factors on combustion efficiency in a flare system. We also go through and talk about the independent testing that's conducted here, increases that confidence level of the parametric model to show it's a reliable method for CE and DRE measurement. And once again, the key thing here is to remember that you need to ensure the net heating value stays above that 300 BTU per scuff minimum, which would lead to operators aiming for continuous monitoring rather than just the current spot checks or one time, whatever it may be, especially where you have flare compositions that can vary widely, like we see with the downstream side. The last paper shows that there's a good match between the experimental data and our CFD modeling, lining out to within about 1%. And the results also show that the MFR effect has more of an impact when your net heating value decreases below that 300 threshold, which can be seen more commonly in unassisted flares. Now that we've discussed the testing conducted on CE and DRE, let's look more at the flare monitoring regulations that we see across the globe. Now, obviously, I just want to say this will differ based on if your flares are located in the upstream versus downstream parts of the oil and gas industry, as well as what your local environmental regulation requirements are. By no means should this be seen as a comprehensive view or recommendation over the next few minutes, but rather it's a refresh and sort of highlighting what we as Panametrics are seeing globally. The Oil and Gas Methane Partnership 2.0 is a multi-stakeholder partnership. It brings together oil and gas companies, as well as international organizations, governments, and non-government organizations to improve the accuracy and transparency of reporting of key to methane mitigation in the oil and gas sector. While OGMP 2.0 does not recommend specific technologies for identifying and quantifying methane emissions and acknowledges that some technologies or combination thereof can be used for these, do have the following verbiage. That process simulation models based on representative flare systems and operating environmental conditions validated by direct measurements and engineering calculations based on studies relevant to the flare condition can also be used to determine the destruction efficiency of the flare. This closely aligns with what the capabilities of flare.IQ are, using the parametric model derived from experimental data and CFD calculations to provide that real-time monitoring of CE and DRE. And just below, you can see the image of that typical upstream flare setup and how flare.IQ plays into the existing system with minimal hardware changes required at a site. Earlier this year, the European Union released their methane action plan. In total, the EU is looking to improve the accuracy of measurement and reporting of methane emissions through compulsory measurement and verification. There are additional effective mitigation measures that focus on the promotion of best practices and legislated standards. So let's take a little bit more of a look at the highlights from those regulations. Article 1 starts off and defines the scope of the regulations to apply to both oil and gas exploration and production, as well as gas gathering and processing. Article 12 talks about the source level quantification of methane emissions and how it should be done in accordance with OGMP 2.0 technical guidelines and measured whenever it's feasible. Article 15 talks about, once again, how flaring should be reduced only for safety reasons. However, flares in themselves won't disappear. They're still required to operate as necessary. It's just the continuous nature of them that needs to be removed. Where, in any case, where a flaring event has less than 99% DRE, that must be reported under Article 23. The big part comes in Article 33, as it talks about how member states will have agencies that have the power to impose administrative penalties and measures for infringement of these articles. All this centers around the opening points in the regulation, where point 43 that we see here focuses on the CE measurement of flaring devices. On the other side of the Atlantic Ocean, we see a little bit more of a split of these regulations between the upstream and the downstream side. I'll just touch on these briefly because while they are somewhat similar, there's a little bit of differences. As we see here, we have what many call the Quad OB and Quad OC requirements. They focus a little bit more and have this minimum combustion efficiency of 95%, whereas the MACT refinery sector rule that we see on the downstream side states 96.5% for CE and 98% for DRE. But we also know that the RSR requirements are basically copy-pasted or modified in some way for a lot of the other regions we see across the globe. Whether that's the Latin America teams that we're seeing start popping up with a little bit of similar stuff, or some of the countries that we have in Middle East and Asia as well are looking to the EPA guidelines here to be able to implement it at their own facilities. So with that, I do want to set up our second survey of the day. This one's going to be another question that will be available for you here. It's going to talk about, it's going to ask you if you currently have a monitoring and reporting flare emission solution. I will have that up here for you guys. So please feel free, let us know either if you have a solution that you like, if you have a solution you aren't too happy with it, and maybe you want to see what other options there are, or maybe you have no solution in mind whatsoever and have just been hit with some of these changing regulatory landscapes as well. So please take a look at that and give us some feedback there through that question that you'll see up on the screen. With that, I'll go ahead and continue just so we can get to our Q&A session here in just a second. We'll go ahead, I'll recap what this means for our operators and regulators for the flare monitoring and control while you're filling out the rest of that survey. Here we have the continuous monitoring is critical. Stack emission factors or spot check values should be replaced by real-time CE and DRE measurements. Our ultrasonic flow measurement is the best available technology for flares and provides a solid basis for parametric modeling utilized by flare.IQ for control and emissions quantification. The in situ nature of CE and DRE measurement from the parametric modeling does not depend on weather conditions or other ambient phenomenon, but only relies on the measurement of the sources that are already monitored by operators today. As we see with the EU's regulations, deflaring provides the least investment requirement for the quickest way for operators to reduce greenhouse gas emissions. It won't be the magical single solution, but it will provide the strongest return on investment as everybody makes that transition. The methane quantification methodology that's implemented by flare.IQ aligns with the OGMP 2.0 Level 4 compliance emission reduction guidelines for CE and DRE, critically giving a light at the end of a very long tunnel for both operators and regulators. For processes where active flare control is possible, emissions can be improved through tighter continuous monitoring. Even on unassisted systems only interested in emission quantification, it can provide a better view into the daily operations of a flare, allowing opportunities to improve system processes in the interest of emissions. The ease of deployment comes in with the existing install base of ultrasonic flow meters that are already installed on a wide majority of flares globally, thereby requiring minimal site changes or projects. And the last part here is the flare.IQ installations have been serving customers since 2017 on a wide variety of applications in both the upstream and the downstream markets. This, coupled with the independent testing conducted at the John Zink facility, provides a reliable solution capable of meeting regulatory needs. I want to say thank you for your time. With that, I want to pass it back to Chris to lead the Q&A session.
Excellent. Thanks very much for that presentation, guys. We'll jump right in. If you do have a question that you haven't asked yet, a few of you have already submitted questions, but if you'd like to submit a question, you can type it into the question window on the side of your screen and hit the submit button. So let's get in here. Somebody asks, what kind of analyzer? Only for methane? I guess beyond that, like what else could be captured and analyzed here?
Yeah, what we've seen as analyzers are essentially either gas chromatographs or mass spectrometers. Mass spectrometers are more common in the US maybe than anywhere else. Gas chromatographs, when there's an online analyzer, is probably the one that we see the most. It depends on what exactly you are looking after. As we explained before, it's only for nitrogen determination or methane determination. there's no need for this. But these are the ones we've seen the most. I mean, GC being number one.
Sure. Okay. A question for Hunter. Does flare.IQ work for non-Panametrics flare meters?
No, certainly. So that's a great question. Obviously, flare.IQ, because we're looking at this parametric model, really we can work with any flare flow meter that is an ultrasonic meter. The crux of what we look at is the volumetric flow, your temperature, your pressure of that gas process, as well as the ultrasonic specific parameter of speed of sound for that process gas. That's where we get to have our special sauce that goes into knowing how we can estimate your net heating value of the vent gas and then be able to know what your entire combustion efficiency is based off of that.
Sure. And one for Gerard. Do I need to shut my system down to install flare.IQ?
That's a very good one as well. Not at all. In fact, there's no need to touch on the field instrumentation. The only communication that we need to establish is between the control system and our flare.IQ. So basically, based on the parameters collected on the on the steady stage, we're going to configure flare.IQ that it comes pre-programmed. It is installed in the control room. And then what the customer will need to do is to map out the Modbus addresses into their control system to be able to communicate between the flare.IQ and the control system back and forth. So there's absolutely no need to interrupt the process. It can be run during the operations of the plant.
Okay. Let's see. Another for Hunter. For assisted flares, do I need to have a UFM on the steam and supplemental gas lines?
Certainly. So that's a good question, right? On assisted flares, so where you have your steam and supplemental gas or enrichment gas, I would say no, you don't necessarily have to have a ultrasonic flow meter or flow measurement there. However, one of the things that we see commonly with a lot of customers is you need to have an accurate measurement of that, accurate across the full range of flow. One of the biggest limitations we see that customers have is on their steam lines, where you may have poorly maintained or maybe not calibrated cells for differential pressure and some other technologies like that. Definitely, we can take in any flow measurement value, but especially if you are looking to minimize and reduce how much steam you're utilizing, looking to save on costs there, or really just looking for better fine tuning of how much additional natural gas you need to have enough energy at the flare tip. Accurate measurement is really where I would say you need to have a focus on. And if you're confident in your measurements, then certainly it does not have to be ultrasonic at that point.
Okay. And this is probably a good one to wrap things up with. How portable is the equipment? And then following up on that, can it be used for temporary installations and easily moved to support maintenance work? And then how difficult is it to maintain? What technician skill level is required?
Certainly. So I'll take that one. The equipment itself is standard as being a rack mount installation. So it's very common, especially from a continuous monitoring standpoint. It's very good for it to be a permanent install inside of a customer's rack, whether that's in a DCS or an abandoned control room, wherever else like that. Certainly, though, we can use it for temporary installations. I know that there have been a few, actually our service team in our Latin America region has investigated looking at maybe helping use flare.IQ in a more portable method to help with spot checks for customers as they're trying to get a better handle on what their facilities currently do. So certainly right now it's designed as being a permanent install, but certainly we have the ability to, at the end of the day, it's a Modbus interaction for doing those calculations. So certainly can be viewed in some cases as necessary, with a little bit of hard work to get that as being a more temporary install. From a maintenance standpoint, the technician skill level really is very minimal. At the end of the day, once the Modbus registers have been set up and the communication exists between flare.IQ and the control room or the logic controller, there is very little that needs to be done after that. But as you saw with some of the screenshots that Gerard provided as well, it's a very easy to use web app or a browser interface, similar to your Wi-Fi router at home as well. So very, very simple and user intuitive.
Okay, great.
What we can add probably is also that the historian is meant to be stored in the control system as well. It's not meant to be stored into the flare.IQ itself.
Yep.
All right. Well, excellent. I'm afraid we've run out of time, and for those questions we didn't have time to answer, we'll be getting back to you via email. And that concludes today's presentation. On behalf of Oil and Gas Journal, I'd like to thank Panametrics for sponsoring today's event, Hunter and Gerard for being here and talking with us all, and of course, all of you for attending. And have a great rest of the day, everyone.
Thank you.